In this video, let's review binary search, which is an efficient algorithm for finding an element from an ordered list. So you have to take note, like it's manipulating an ordered set, ordered list. So it is cutting iteratively by the problem by half. So the way to visualize this is if you have an original given elements, it will divide it into half, and it will discard, so it will just choose the middle term. And if the query, say the x is the query, if it is greater than our mid term, so middle term, say a sub mid, then we know that the query is in the upper half. So if this is true, then we have to abandon the first half and focus on the upper half. So if we have the upper half now, then we will simply repeat the process. Get the middle term and compare the middle term to our query. If our query is greater than our middle term, then we're going to abandon the first half. Else, if this is false, that means if the middle term is for example greater than our query, then we have to abandon the upper half. So to give a specific example, let's take the example from the textbook by Kenneth Rosan. So you have 1, 2, 3. Again, it's important to note that the elements here are sorted. So you have 1 up to 22, but there are just 16 elements. So first off is to choose the middle term so that we could divide the elements. So we could do that by manipulating the indices. Say we have here the index of low is 0, the low index. How many elements are there? 1, 2, 3, 4, 5, 6, 7, 16. So the last element is 15, index 15. So this will be our high. So first off, we'll get the middle term, which is, we know this to be 1, 2, 3, 4, 5, 6, 7, 8. So this is our middle split. And the way to get the middle split is to solve for mid, which is the low plus high index divided by 2. So 0 plus 15, well, we get a decimal number, so we need to apply, say, floor. So in this first instance, you have 0 plus 15 over 2, and floor of that you will get an index of 7. So that is basically this element here, 10. So 0, 1, 2, 3, 4, 5, 6, 7. So our middle term is 10. And if we perform now the comparison, so the comparison basically is is our query. Say we're going to search 19 here in the example, and is x greater than our midterm? So is 19, again 19 is given by the problem, it's greater than 10, which is in this case true, then we have to abandon the first half and focus on the upper half. And the way we're going to do that is by updating the index. So if you're assuming an array, we have to update the index. In particular, we have to update the low index. So the low index should be updated to be able to choose this upper half. So updated to what number, what value? So if you're going to focus on the upper half now, so let's erase this for now. So we have the lower half and then the upper half. So the old low is 0. So that is 0. Now, since we are abandoning this first half, we are going, and this is a10, or this is a sub 7, is the midterm. Then what is this? This should be the new low, which is equivalent to mid plus 1 with respect to the index. So if the middle term is initially 7, a sub 7, then our new low will be a sub 8, which is 12. For the high, however, high will remain to be 15. So as long as we do not change, this will remain to be 15. So high is at 15. That will remain to be at index 15 as long as the inequality is satisfied to be true. So that means the query is greater than the middle term. So now let's focus on the second set, the upper half, and we will get, so with this upper half we'll get again the middle term. So we'll simply repeating the formula that the mid is basically low plus the high over 2, and let's just floor this one to take care of odd even scenario or odd scenario in the numerator. So this will become 8 plus high will remain 15 over 2 floor, so 23 over 2 giving us a floor, giving us 11, and that is what number? So 8, 9, 10, 11. So we're going to divide it here, and that term is 16. Now the inequality is our query greater than the middle term. So is our query greater than the middle term? It's 19, greater than 16, and this is again true. So greater 19 greater than 16. So again, this is true. Therefore, we have to choose the upper half once again. So you have to choose the upper half, and again abandon the lower half. So in each move, in each iteration of the loop, we are effectively dividing a problem into two, making it half the original problem. So this new low now is equals to mid plus 1. So initial mid is 11, so this is plus 1, low is equals to 12. High remains at 15. And let's check again the middle term. So the middle term will be low plus high. So it will be 12 plus 15. Over 2. And this 27 over 2. So giving us 13, floor 13. So 12, 13. So we're going to cut this into 2. And the middle term is 19. After that, we compare once again. So is the query greater? Is x greater than the middle term? So is 19 greater than the middle term? Now is also 19. Again, there's no equality here, it's just greater than comparison. And this is now false because they're equal, so 19 is not greater than 19. So if the inequality is false, then we have to choose the lower half. We're going to instead abandon the upper half. So abandon the upper half and choose the lower half. So giving us okay, so let's just clear this. So abandon this upper half, giving us the lower half. So take note that this is 18. What the index said. So if this is 15, 14, 13, 12. So the low is 12 and the high is 13. Again, if we check the middle term now, so the mid is equals to low 12 plus 13, and that is over 2, floor of that. So the middle term now is 25 over 2, so this will be floor of the 12.5, so 12. So it will now choose 18. So this is now 18, and so these are just two elements, and we are almost done with this particular process since 12. So we're now going to compare x, the query, is it greater than the a sub 12, which is in this case is 19. Is it greater than 18? And this is true. So if this is true, we're going to abandon the first half and focus on the second half. So this is just the process of binary search, a repetition of this. So therefore, we have 19, the last element. And in this case, after this, we are going to update the the low, for example. So the low is equals to mid plus 1 becomes 13, and this is equals to the high, which is equals to 13 as well. Thus, if we are going to iterate this, this is the termination criteria. You have when low becomes equal with high, and we're going to repeat the process as long as low is less than high. So let's come up with a pseudocode for this. So pseudocode. Initially we have, say, binary search. Let's just come up with an implementation for this along with the pseudocode. So binary search, I'm going to take in an array of elements. Again, these are sorted list of elements, and I need a query X. So for the input here, you have A composed of, say, integers, say A sub 1, or what is this? So A equals A sub 1 up to A sub n, and these are integers, not just integers, they are sorted. And you have another input is the query, of course. So for the output, we need the location. I need a location lock. Let me just call this LOC, location. And the way to divide the problem into two is to play with the indices. So for example, in the body of our algorithm, we have to decide a low index, for example. So this is indicating the start of the list, say 0. Let's just use the convention, assignment convention. And for the high, let's assign the highest element. So if there are n elements, then this is n minus 1. I started at 1 in this particular input, so let me change this to 1. And after this, we're going to iterate. So this will be a while loop. So while low is less than high, and this is remembering that our termination condition from the example is when low became equals to high. So when there's one element left, say 19, low is equals to high, and the terminate should end, or the loop should terminate. Okay, so we have to get the middle term. So mid is equals to low plus high over 2. And again, we will get the floor just to take care of odd numerator. And we will compare. So if the query is greater than your middle term, then you are going to update the low. So you're going to choose the upper half. So low updated to, so update the low to mid plus 1. Else update the high. So the high will be updated to, let's just update the high to be equals to the mid, because that will be the last term. Mid is the last term of the first half or the lower half, and that's it. So after this, let's end if, and let's end while. So end while. However, we have just one element left, so we need to check whether we need to do one last check whether the element is found or not. So if the last element, so if the element that was left, that means a sub low, or you could use a sub high because they are equal anyway, is equals to the query, then that means you have found the element. So you return you return the index, or in that case I will simply return low for the location. Else, so else not found, or return -1. And again, the -1 is for when the element is not found. Okay, so let's come up with an algorithm for this binary search, and its input elements. Let's just define the size of the array for simplicity, and let's just use the example, say 16 element array, and a n, for example. Query is an integer x. So first is assigning a low, so int low and high. So let's assign it, low is 0 and high is n-1. Now that I think of it, for the algorithm earlier, this should be 1 to n if we are starting at 1. So if we started at 1, this should be, so the code should be from 1 to n. But if you're starting at 0, this will be from 0 to n-1. Okay, so just a slight, this is a return, so int okay, so after that there will be a while loop. So while And then the condition for termination is while low is less than the high, you're going to continuously compute the middle term, which is the floor of the low plus high divided by 2, and we're going to perform a comparison now after getting the middle term or middle index. So if the query is greater than your A mid, okay, then update the low. So low will be now mid plus 1. So you're effectively choosing the upper half. So choosing the upper half. Else, we're going to choose or update the high, effectively choosing the lower half. And when that terminates, we're going to perform one final comparison here. So if what's left, the element that's left, is equals to the query, then we can return the location of that term as being found. So else, let's return -1. And again, this is for not found. So let's take a look at this. This is an integer array for simplicity. So we have now defined a function. Mid is not declared, so let me declare it. So our function is binary search. It accepts an array of elements in the query. So to divide the elements, we need its index for the starting point, the low, and end point, the high. And we started at 0, and that explains why it is 0 to n minus 1. And we will continually reduce the middle term by computing the middle index and applying the floor, and then comparing the query to the middle term. If this query is greater, we are going to choose the upper half, choosing the upper half by updating the low index. Otherwise, we will update the high index, effectively choosing the lower half. And when all is done, we have one element left, and that one element will be compared with the query. If it is equal, then we have the location, it is found. Else, we simply return a negative value for not found. So let's apply this to our given set from the example. What is this? 1, 2, 3. Okay, can I choose this one? So 1, 2, 3. Anyway, let's just type this. So int array, and I have elements 1, 2, 3, 5, 6, 7, 8, 10, 12, 5, 6, plus 13, 15, 16, 18. I think there's a 19 and there's a 20 and 22. Did I get that correctly? Okay. So are you 16 now? Okay. So now let's apply the binary search. So say binary search, so the location printf, if you get the -1 location, then it's not found. So the location of query, so let's have a %d query is another %d or index, and let's input, say query is x, and the location will be the result of binary search given the a and x. So I have to put an x query here as 19, for example, and we know the location of 19 to be 15, 14, 13, so this should output 13. Okay, so let's try to run this. Okay, so the location of 19 is 13. Let's try an element that is not found, or let's try the last element for now. So the last element is, say, 22, and its location should be 15. Okay, so we have a location 15. Let's have not found, say 21. 21 is not there. So we're expecting -1. And -1 it is. So that's it, a very efficient searching algorithm, the binary search. And as you can see, we could directly translate that from its pseudocode